So remember what we did yesterday. I'll show the slides so we go faster. Play. Voila. Okay. So what we said yesterday was that when I go and calculate x plus 1z, dft, so in this blob here, I can use a contact interaction or I use the loop. And what we showed yesterday was that the standard model goes down and the EFT has a stronger high energy behavior, right? It grows, the amplitude grows with the square root of s over v, is a dimension 5 operator, effectively. So the amplitude goes like square root of s over 1 power of the high scale. So the amplitude squared grows like s over v squared. Okay, so there was a comment also, again, one from you, and said, well, this thing, right, and high PT might not work well, okay, because it's here instead of here, but if I have, again, some kind of new state, which is heavy, right, and possibly decoupling, like squarks, then I can still get new physics information from here. So not from the standard model, but imagining now that I have an operator, which is the one which we mentioned yesterday. Okay, so I have an operator like this one, which is now generated. I mean, I think the standard model as it is. I add the dimension 6 operator from new physics. Okay, so I have this operator, and then what I said is that you might also have a change in the Yukawa. So this one, we call it O T phi, and this one O G phi of phi g. Okay, so we have two operators. And then what I want to do is that, okay, I might have these two operators. So what should I do to constrain them? So how do I use data now to constrain these two operators? So then you would say, well, I look at the cross-section for producing a Higgs. Okay, and I calculate the cross-section in the EFT. So I compute sigma EFT and divide by sigma standard model. So there is a term 1 plus a number times the coefficient of C phi plus a number which is the coefficient of T phi squared, for example. So how do I get the number? So I calculate this diagram. So the blob now means Ct phi here. It's the same diagram at the end in the standard model, but remember, I'm unlocking the mass with respect to the Yukawa. So this is exactly the same as the standard model. Okay, then the number depends on the normalization of your operator. And Cg phi, I calculate it in this way. Okay. And then if I want, I can also modify the coupling of the bottom, if I want, right? And add that contribution also. I'm not doing it for simplicity. So if I do that, what happens? Okay, let me say another thing first. Also, remember that keep in mind that the normalization of an operator in this math has no meaning in first approximation. So the normalization, how I normalize an operator in front is a UV condition. So if I want to estimate the coefficient, I have to have in mind a UV completion. If I want to be model independent, there is no special normalization in front. Okay, so now in this math, we have a conventional normalization, which means we don't write anything in front of the operator. So that's a convention, totally without any meaning in itself. Okay, so keep this in mind, it's important. So these numbers are somewhat arbitrary by the normalization. Okay, I'll explain how it works then, because then you say, well, if they're arbitrary, what am I going to do, right? But I'll come to that in a moment, right? So keep in mind that these numbers are normalization dependent. So you should not say, this number is much bigger than this one, and this has a small sensitivity. It's not the way it works. Okay. Okay. So so you do this. You compute the two terms there, and then what next? Well, you compare with the data, right? You compare. You look on your data measurement. You divide by standard model prediction, so you get 1 plus something. But then what happens to your determination? You have what is called a flat direction, because you have a linear. This can go up or down, right? So you have an ambiguity. You cannot close the system. You have two variables and one number, right? It's rather obvious. So this is explained here, if you want. So you add the two diagrams, right? One from the Yukawa and one from the Higgs. There is another one which is called Chromo. I'll come to that in a moment. But what you see from here, right? If you compare with data, you see that there is a flat direction. So that's why it's called flat, because this is a linear system. So the directions which are not constrained are lines, are hyperplanes in this space. So you see that there is a flat direction here, okay, where obviously, right, if I check this, you see the scale is different, but if I rotate, right, so at the end, you're only sensitive to this thing here and not to the orthogonal one. Okay, that's rather obvious. So you say that your fit has a flat direction. So how do you solve the problem of having a flat direction? The only way is to add another observable which does not depend on the same linear combination. Because if it depends on the same linear combination, right, you're stuck at the beginning. So which one? Which is the natural candidate now? Where the two processes enter in a different way? This one, right? Because we just said that these two curves are different. So if you make a fit, right, and you use the information from the mean, if you only use the information from the mean and low PT, you don't solve it. But if you use the information on the mean from high PT, you solve the degeneracy. Is that clear? Because your cross-section at high PT as depends, right? So you do like the same, will depend on a different linear combination, okay, of CG plus OT phi. So that's the logic that we use to make fits in the EFT. We find enough observable that depend on the coefficients in a linearly independent way. Okay, so this is a very easy example to understand the logic. So if you have n operators and you do a linear fit, so you don't include the quadratic terms, which we discussed, becomes model-dependent question whether they are reliable or not, unless they are very small and they don't matter. So if you do a linear system, if you have n observables, at the end you need, if you have n operators, at the end you need n observables, to say the least. Okay. Then what we really do, we put many more observable in the fit, right, as usual, and then you check whether your system is still closed, right? So technically, each bin of this distribution is an observable, okay, because is a correlated, because there will be correlated uncertainties, but each information, if you have a plot, right, each bin of the plot is one observable, okay? Yes. Right. Yeah. Yeah. So, rightly so, you're asking whether we can close the fit, really. So we never do, in practice, we never do when we say that we do a global fit, it's never global in the sense of 2,499 operators. Okay. We always make assumptions. And where we do make assumptions most strongly is in the flavor structure. Because the flavor structure of the SMEF is totally, if you want, very, very rich, okay, because you have all combinations. So you need flavor assumptions, some kind of symmetries that we use. We use very simple ones, right? And this reduces the operators around 100, okay? And then we have enough observables to do that, okay? Also, because of this thing here, that each distribution is actually bringing different different information. So now let me complicate it again, okay? So now I have two observables and two unknowns. So let me now add one further operator. It's called the chromo operator. So it's a it's a different one. So it's a dipole operator. So there is a color matrix somewhere. Let me put it here. So this is a dipole. It's the same that Ian has shown you. Ian showed the weak dipoles, the W and the W and the B, I think. And this is the analog one, but with the strong interaction. Okay. So this gives rise to an anomalous interaction. It's a very interesting operator because so this is a color matrix. Okay. So don't be confused with the top. So this is a top right. This is a top left. So it's like a Yukawa from the point of view of chirality because it couples the left with the right of the top. And also it couples to the field strength of the gluon. So if you now if you think that this phi again as a component which is age v square root of 2, when you hit the v, the vacuum expectation value, there is no Higgs anymore, it's a constant, and it becomes effectively an operator on dimension 5, okay, which is the dipole that we study normally in QCD, right, in school. So this is the dipole, and then since there is a chirality flipping, anything that comes out of it becomes proportional to the mass of the top, basically, okay? But when you have the dynamical Higgs, then you have a very strange coupling. So if you have this kind of coupling, which is new, but you also have this coupling, right? Where does it come from? It comes from the fact that in G there is the commutator. It's a non-abelian theory. So in the field strength, you have the commutator of two fields. So this gives a coupling, like this Seagull kind of coupling, right, which we are used to in scalar theories. Now, at higher order, we also have it in a fermion theory. So you see that there are two coupling, but there is another one also. It's kind of cute. is the one where the Higgs is dynamical, and you have a coupling like this. So the one where the Higgs also couple there, and then another one. Okay. So this one is a coupling which is somewhat new. It takes together the Higgs, the gluon, right, and the two quarks. Yes. Yeah. Yeah. Yeah, because you can go up to dimension 6. Each boson is dimension 1, right? So this is dimension 5, and you also have a dimension 6. So a 5 point here because you have a fermion, right? So you can't, by counting the dimensions of the fields, you know up to which number of interaction you can go. If you have two fermions, you can go up to 5-point interactions, right? If you have all bosons, you can go up to 6-point interactions because they count the number of dimensions of the field. So it's very easy. And then you get all the lower one, okay, by adding powers of V. So this has a derivative, right? This is a power of V, and this has 1 power of V and so on. So you compensate so to have all the stuff in the right dimension because everything has to be divided by lambda squared. Okay, so the chromo is a very interesting operator. And you see now that if you think about this way of thinking, then you also have, for example, diagram like this. Oh, let me draw it. I don't know how to draw it. Okay, artistic way. So you have one X that couples directly here, or you have different ones, or you have this one. Okay, where this is a vacuum expectation one. So the contribution from the dipole are drawn there, if you want, are different of different nature. There are different diagrams that contribute. So remember what I told you last time? I told you that if you are in a renormalizable theory, and we'll use this again today, if you are in a renormalizable theory in dimension 4, and you calculate a loop of something which is not there at the Born level, this loop is finite. Well, it turns out that then you would say, well, this is finite, but this I know is finite because it's just the same as the standard model. I only scaled y, so it's certainly fine. Here there is no loop. So here, is this finite or not? The answer is no. Okay, this loop here is not finite. So it's the first time actually that in such simple setting you realize that this loop here gives a divergence in the ultraviolet, which is actually reabsorbed by renormalizing the coupling at 3 level of the EFT. Okay, so it's all consistent. There's no problem, right? And one loop, you can reabsorb all the divergences, but you don't reabsorb it here. You need the other operators to reabsorb it, which is what in the EFT is called mixing, right? All the operators, when you lower or higher the scale, start talking to each other, which means that to renormalize the contribution of one operator of one loop, you also need other operators in your basis. And that's why you need a basis which is complete. And in that sense, an effective field theory at a given order is renormalizable. Okay, because it means that at any given order, we can reabsorb all the divergences that come out in one loop with one insertion spread among all the operators of your basis. So order by order in 1 over lambda square, the SMEF is renormalizable as the dimension 4. Okay, so that's what changes the perception a bit, right? It's renormalizable with respect to the gauge interactions. Okay, you don't you cannot put more than one insertion in your diagrams. But if you only put one maximum, so you strictly stay at 1 lambda over lambda squared, your theory is renormalizable. So you can compute any number of loops you want, and you always will never go out of this basis. Okay? So that's the reason why it's improvable as any other theory. Okay. Very good. So what happens now, right? Then you will say, well, now I add this other operator, I'm stuck again because I need 3 observable, right? So we did this. So I personally also played this game. So first of all, this is the fit that it closes when you add high PT with 2 operators. But then if you go on, right, you need a systematic approach, which is what I was telling you before. So what we do is what is shown in this slide. So let me erase here. So what we do is that we define an observable, and we compute the observable. So we determine the observable experimentally. We subtract the standard model prediction. So this is theory, but from the standard model. And this difference is proportional to, parametrically proportional to coefficient which are calculable in perturbation theory. These are the diagram which I compute putting one insertion in each of the diagram like I did before, times the Ci, which are the Wilson coefficient. Okay, so this is computable perturbatively. So the diagrams, let's say, okay? So, for example, in the case before, we compute this one, right? One diagram, one new physics insertion, only one. So all these numbers are like m squared, cross sections, whatever, observable, computed in my EFT. And then I build a system, right? So this is, you see, is a linear system now on the left. My unknowns are this Ci. Okay, these are, I know, is a linear system where I know all the coefficient, and then my unknowns are the Wilson coefficient. So obviously, if there is no difference here, like now, roughly speaking, okay, then all of the Ci are 0, which is basically the situation we are in right now. Okay, we don't see any, if I want to simplify, any deviation here. However, what I really see, what I really do when I do the fit, I have it's not 0 that counts right now, is how close to 0 you are, right? That we determine, and that's a useful information. Of course, we all know that we don't have any evidence for any of these Ci's to be different from 0, but the way we improve our work is to get the uncertainty band around 0 smaller and smaller, and that's what we call sensitivity. Okay, the uncertainty, final uncertainty in this determination, they are all 0 in all fits, but what we struggle with, we strive for, is reducing this uncertainty. Yes. So what, within the uncertainty, right? You don't know, but if your system is constrained, right? You get all zeros within an uncertainty, all of them, because if this was not, I mean, you can compensate up to a given point. Why? Because the system is not. There are no flat direction. here I'm assuming what you are saying is true if you have a flat direction. So you can, right, imagine that two of these coefficients everywhere appear with the same linear combination. Then you don't constrain each one of them, you only constrain the linear combination. Now we are saying that the determinant of this linear system is non-zero. So we have to get to that point. And to get to that point, you have to have enough observable to be redundant enough not to have that problem. But if the determinant is not zero, technically, that's it. Okay. Okay, so this is the idea. Of course, there are a lot of, so I'm simplifying maximally, right? There are a lot of points where you have to dot the i's and so on, because there are 1 over lambda 4 term. You can have the quadratic term. If you have the quadratic term, you can easily prove you have no flat direction by construction, because there is no way of having a degeneracy, because they're not flat direction anymore. They're curved, so there are no more flat direction. So there are the theoretical uncertainties, the systematic uncertainties, the correlated uncertainties. It's very complicated fit at the end to do, but this is the logic, okay? So what you really want is to have the most precise measurement, the most precise prediction for the standard model. It's critical to have the most precise prediction of the standard model here, and the most higher possible degree, because if you if you get this wrong, okay, then you are going to absorb into the SMEFT higher order your inability to match these two. So these have to be matched the best you can, right? So you understand it's different from the accuracy with which you determine this coefficient. This is less important to some extent. This is critical, because if you don't get this right, you're gonna artificially enhance the new physics terms on the right. Okay, is that clear? So yesterday there was this question: why we do the FT and we just don't test the standard model right away? I mean, just check whether the mass of the top is the same as the Yukawa from TT bar X, for example. The reason is what I'm trying to explain today, that if you do this game, you're really deforming the standard model. So this is a linear deformation of the standard model, parametrized in a gauging variant and systematic way in higher orders. There is no, the arbitrariness that you might feel is very much reduced with respect to arbitrarily changing any coupling randomly in the standard model. Okay, here you can compute loops in a consistent way in all, here in the red blob and in the green blob too. Okay, so you can improve it systematically in a consistent way. So I have a, one way that I have in my brain to represent it, where the sensitivity comes from. So imagine that your current measurement are the blue dots, and your red is the theory prediction, right? So you measure many observable, and statistically, not all observable come within 1 sigma, 2 sigma. Some one go higher sigma, okay? But you have many 1 sigma or 2 sigma deviations, and each one of them is not significant, right? If you look one measurement at a time. But what does the FT do really? It correlates them, okay? So it is predicting a pattern in the deformation. That's what it really does. So now if you have a pattern and you deform them, so these fluctuations within the SMEF are not random anymore, okay? So even if each one of them can be 1 sigma or 2 sigma, together they might get a better sensitivity. You see? So that's the power, because you are building correlations. You are really correlating various observable among themselves in a linear way. Is that? Yes. They're not. I know they are not. And what I do, I build a correlation matrix for the measurement, which I know how they are correlated. So, for example, in the I told you before that a distribution has many observable because each mean is an observable. But of course, in a measurement of PT, this is correlated with this one because some systematics like jet energy scale go the same way in both means, right? So you have for each measurement, all these mean are actually metrics, okay? So you don't get n numbers, you get n squared numbers because you also need the correlation matrix for the uncertainties. So you increase, right? You increase your sensitivity to new physics using this correlation, which is somewhat the shadow of your UV in UV model in high energy, right? So it's a kind of poetic way of saying the usual thing, right? That somewhat when you evolve it down, you switch on some of these operator only. They are all correlated from your UV theory. And what you're really studying now is the correlation which is imprinted in low energy from the UV. Okay. So so we take back, so now I told you, right? I added this third operator here. And now my game has been, now it gets more complicated. I need more observables, right? And so I need to combine various observables. So now I'm combining the X, as I told you before, X plus Z. And now the obvious one which we were missing is, of course, a determination of the Yukawa. And the best way to determine the Yukawa of the top X and the LHC is this cross-section, which is around 100 femtobar. It's called the TT bar associated X production, which is, you see, directly sensitive to YT squared, right? When you, the cross-section, the amplitude depends on YT, I square it, it comes directly proportional to YT. So that's what I call, so stay with me with the lingo now. I call this determination of Y ideal, right, direct, because it's classical in a sense. You compute a cross-section, right, and you compare a number of events with your prediction, and you get YT. Now, it's not true really, because we don't measure this, right? The X has to decay. So the number of events that we measure is always sigma times the branching ratio of the channel that we are looking at. So imagine that this is goes to gamma gamma, right? So this will be the cross-section for TT bar X times the branching ratio of X into gamma gamma. Okay, so the game is actually a bit more complicated than this, and now you realize why extracting information from on the X and the H is complicated. And it's complicated because each signature depends on the branching ratio, and the branching ratio is sigma, right, gamma partial divided by gamma total of the X, right? Branching ratio, gamma partial divided by gamma total. And now you see what is the catch, right? The catch is the gamma total depends on all couplings of the X. Not all, but many. Okay, because the X can decay into tau tau, glue glue, TT via loop, mu mu, I mean, all decay rates, right? So hidden here, all the coupling of the X are hidden in the partial width. So now it's obvious that from one single measurement, I don't only determine these two effective coupling YT squared and X to gamma gamma. Actually, X gamma gamma, I know there are two diagrams. So it's a non-linear system at this point. Okay, so that's the reason why it gets complicated. But it doesn't matter right now because once we understood that, then you write a code that does it for you. Okay, so it's not There is nothing conceptually challenging here. Okay, so remind for this now, which it will be useful later. Um, remember that the Yukawa determination from T bar x, I call it direct. Direct means classical, in the sense that the probability of the event is really related to the coupling I want to measure with the square. Yes. Absolutely, absolutely. Very good idea. That's what we do. So, for example, so what I really want to do here is to have another channel, right, with also goes to like VBF, for example. It's not a good example. No, sorry. Let me take like glue, and then to gamma gamma. And then I take the ratio of these two. Then in the ratio, I will eliminate the branching ratio to gamma gamma. Okay? So that's one way I can, but at the end I do a fit, right? Again, we are just doing a fit. Okay, so how we do it? So then you say, cool, right? This is one complication. Let not think about it for a second. So let not decay the Higgs, okay, for a sec. So this is the Higgs. But now I look at this process, right? So this will be sigma T bar h. I divide by the sigma T bar h in the standard model. So I get 1 plus the Yukawa, right? So there will be a Yukawa contribution, so a number time T phi, plus what else? Does this operator contribute here? Let's see if you are following. Does this operator contribute to this process? 3 level. Yeah, it does, right? Because now you can write a diagram like this. So it does contribute. And there is also another diagram like this, for example. There are a lot of diagrams, but again, no problem. There is a computer for you that does it. Okay, it's only understanding what you have to do. Okay, so this contributes. So I will have a number which is g phi divided by lambda square. Okay, and what about my friend the chromo? Yes, right. Of course, because you can have a diagram like this, which is actually enhanced at high energy, because the more legs you have in a vertex, the more the behavior of the diagram grows with energy. Okay, so this grows with energy strongly, while this one doesn't, for example. So this is more important than the others. Okay, so then you have. So this is not. So this is a symbol. It's not the. It's not the Lambertian. I don't know. Let me call it this way. And then you have C T G over lambda squared. Okay. So they all contribute with one insertion, which is my current accuracy in 1 over lambda squared. So I have to sum them all. And I have to see, right, whether, for example, if I get different direction constraint from the different processes. So how do I do it? I look at the coefficient AG, and well, the naming here is different. Forget the naming. But basically, you go in two-dimensional plane, you check that the constraint from TTH are not aligned with the constraint from PPH, and that means that you are breaking a flat direction. Okay, so you keep going, and you do like that. Okay, you got the logic? Then you put everything together, right? So you have tt bar x, pp bar x, age x, and all of them contribute in a different way. And then you combine all constraints. Here they are not linear, so I'm also using the quadratic term to determine this. And you find, right, the constraining power on this operator from these different processes. And that's what we are doing, okay, with this method. Yes? Mm-hmm. Yes? Yes. So your question, I repeat for everybody. So um, we are wondering if there are subtleties with higher orders in 1 over lambda square. The answer is yes. There are subtleties everywhere. Okay. This is, I'm trying to explain to you the logic, the basics, right? It's very, there are a number of subtleties which I mentioned already in this formula, right? I'm ignoring, so this is linear, but I'm ignoring dimension 8 operators, which enter in 1 over lambda to the fourth, and I'm ignoring double insertions when it's possible to have double insertion. Here, for example, you can have double insertion because you can also modify. So this one is a new physics coupling, but you can also modify this one if you want, right? Because I told you that the chromo changes also this one, okay? So if you want, you can have two insertions here. And then is dimension 1 over lambda 4 if you interfere with the Born. Also, remember that this diagram, when I square them within the standard model amplitude. No? Right? Because the 1 over lambda square term is A SM times A EFT. One insertion here. But you see that I can do two insertions in two different ways. I can put two insertions here, or one insertion here, and one insertion there. These are technically two different things. Okay? If you do two insertion, is really doing dimension 8 operator equivalent. If you're doing one insertion here and one insertion there, is what I technically call the square of the diagram, which we discussed during the discussion session yesterday. So these are two different classes of 1 over lambda fourth contribution. So, yeah. Yeah, we expand it linearly. Okay, so the everything is well defined and consistent if you expand linearly. Then you don't make any. That's the SMEFT, vanilla SMEFT, right? You have a dimension 6, you expand linearly. Nobody can tell you anything about that. You are safe and you are consistent. Now, at the end, though, you have to check whether what you get makes sense or not. And that's where the problem arises. Okay, when all these subtleties arise. Anyway, okay. In an ideal world, you have enough constraint and accuracy is sufficient that by stopping at 1 over lambda 4, you get all the constraints that you want, and all you can show that all these higher orders are small. Then you are in the ideal SMET case, and everything is defined and solid rock. But if some of these terms are not small, or the uncertainty in the experiment are not such that you cannot constrain and so on, if, then it becomes more complicated. Okay. Okay. Do you have any questions? So at the end, right, what you do, you build you mean a map of operators which enter in various processes. You see, I mean, for example, the coefficients that we were discussing are here, and are related to the Higgs. so are in the X box. But this can also be in the top box, for example, some of them. For example, HT is in the top box here. So depending on which observable are, right? For example, this one are in all the boxes. Okay, so they can be constrained by many measurements and so on. Some operators, and we will talk now about one special one which is especially important, is you can only get from one measurement. Okay, for example, if you want to determine the Yukawa coupling of the X to the muon, and then let's see, we have only one measurement that can do that, which is the X decaying to mu mu. We don't have anything else. So you see that from the point of view of the fit, if you consider the X coupling to the mu or not, doesn't make much difference, because if you do, you add one observable, and if you don't, you take it out, so the system is almost nothing happens to your fit. Okay, is that clear? I just want to explain the logic. Then there are many details, and you are free to ask any doubt that you have here or later. So now let me slightly change topic. Not really, but I mean specialize on one aspect. And the aspect I want to discuss in detail, because it's very important for even on how we are deciding our future, as we were discussing before, is the Higgs self-coupling. So the Higgs self-coupling comes from the potential of the Higgs. So we said already, right, this is the only dimensionful coupling entering in the standard model at the Lagrangian level, mu. And mu is related to the vacuum expectation value and lambda, right? But basically, the way to think about it, right, is that mu, once you know once you know V, you fix mu. Okay, so that means that there are two parameters here. One is low energy, V, which you get from a muon decay. So I know it since a long time, right? As we said yesterday, square root of 2 GF is equal to V to the minus 2. So we know it from back then, right? From the beginning of the Fermi interactions. So this one we know. The one we didn't know was lambda. But as you remember, right, the Higgs mass depends on V in this way. So once you know the Higgs mass, we learn lambda. Okay, so two parameters, two constraints. One constraint, one here, we know everything. So in the Higgs potential, there is a two-dimensional free object, and we have learned everything now that we know the standard model. So how do we write this potential? So we again, so this is a textbook exercise, right? We do it in the standard model course. We put the unitary, we go into unitary gauge, and then we substitute, okay, with this constraint. So this constraint is the minimum. This is telling me that the minimum of this potential is at V, and I impose it, okay? So I'm already using it. I don't have to impose it again. So I just substitute my expression. So there is a minus. So in some notation, here there is a plus and then there is a minus here, but it's the same thing where you put the minus, okay? But remember that at the end there is a minus here, okay? So I substitute mu square from here. Mu square is lambda v squared, I put it here. There is a minus, and then I substitute the doublets. So here is a square, and here is a fourth power. And then remember what, yes? Yeah, thank you. Yeah. So we do this, and then what do I get from here? I get automatically that the linear term in the potential is 0 because I use the minimum condition, and I get the mass of the X. So the calculation is trivial. So I get 1/2 mass of the X squared plus lambda V X cubed plus lambda over 4x to the fourth, where m squared is this number here. So I read it off, right? When I develop here, I read off from the Lagrangian what is the mass of the Higgs, and the mass is this one. Okay? I read it from the Lagrangian. I don't impose it. So now this means that you can rewrite lambda as mx over 2v squared from there, right? And now you express the everything in terms of what you know from experiment, mass of X and vacuum expectation value. So you put it back here, and everything is expressed now in terms of the mass of the Higgs and the vacuum expectation value, right? You eliminate lambda, okay? So lambda is derived from your inputs. It's not a free parameter anymore. So this we said yesterday. So the way we say it is that lambda 3, which is this coupling here, is equal to lambda 4, which is this coupling here, and is equal to lambda, right? So let me, if I write, a low energy version of the Higgs potential, arbitrary, I can write it in this way. Okay, so imagine that I build an arbitrary theory, and this I call lambda 3 and lambda 4, and the standard model predicts that lambda 3 is equal to lambda 4 is equal to lambda, which is equal to mx over 2v squared. And this yesterday, we called it locking. Okay, so the couplings of the X to itself are locked by the mass of the X itself. There are no free parameters entering. Everything is determined in the standard model. Okay, so now I want to know whether this prediction of the standard model is valid or not. Right? So what do I do? The mass of the X I measured, I know, from the invariant mass peak of gamma gamma or X in 4 leptons. And it's 125.09 GeV. We know it very well. So that's one thing, and I know. Then, how do I test this theory? I need a process which depends on lambda 3. Okay? Depends on lambda 3 and or on lambda 4. Okay? Okay, so which process this will be? Well, I will need to test the self-coupling of the X, imagining that one of these X's coupled to something, then I need 2X in the final state. Or I need a process where I fuse 2 Higgses into one, right? But I need something like that. So the main way to test the self-coupling is what is called 2x production, where I have 2 Higgs bosons in the final state. Okay, this is one way. Okay, so this is at 3 level. Otherwise, what I could do, okay, is to have a process where I have like 2 Higgses that fuse into 1 Higgs. That's also possible. Okay, and this can happen either at 3 level or at 1 loop, for example. In fact, you see very quickly that the LHC, this is not possible. So there is no significant process cross-section for anything that can do that. Right. So, for example, let's imagine one process where this could happen at 3 level. Let's see if you can imagine it. Anybody? That this can happen at 3 level? Well, for example, we remember that we did 4 tops. No? So if I have 4 tops, this could happen. Right? But this is so 4 tops, the cross section for 4 tops is 10 femtomer, super small. This cross section is weakly suppressed with respect to that. Super tiny cross section is never, you will never get to that. Okay, so this cannot be done basically in the LHC. So we have no way of testing self-interactions with 1 Higgs at 3 level, but it's possible. Okay, what I mean is that technically, if we had enough energy, enough luminosity, blah, blah, we could do this at higher orders in the final state. But we don't. So this is not, I mean, it's not practical, let's say. Okay? So this is not in our realm. So let's go back now to 2 Higgs. So I want to notice one important point now. So let's imagine a process where I produce 2 Higgs. So the easiest one is to think about gluon fusion. So I know it's not 3 level, and that's the reason why I use the quotes, but it is a leading order process, right? And we knew by experience that in the case of single Higgs, at the end, this is the most important one. So let's think about this one first, no? By extension, let's say. And it's true. This one is the largest cross-section, production cross-section for double Higgs at the LHC. So we are not wrong to think about this process as the leading process. However, so it's leading order, even though it's 1 loop, but it's the first time it appears, so it's leading order. And given that it's the first time it appears, this calculation is finite. I learned this already. I don't have to do a computation to be sure. I'm confident that this is the case for sure. Now, what is the main difference between this computation and the one before? Well, you see there are 2 classes of diagrams, right? There are many here, right? You can attach the gluon where you want and so on. So what is the main difference? Is that there is only one class of diagrams which depends on lambda 3. This does not depend on lambda 3. Okay? So this the cross section for sig xx has a piece which is like, let me call it no lambda 3. Then there is a piece which is lambda sigma hh linear, right, in lambda, and then we'll have a piece which is quadratic in lambda. So let me call it 0. Okay, it's more professional, right? In lambda when expanded, because this guy has no lambda 3. This one, the interference will have 1 lambda, and then the square of this one will be quadratic in lambda. So we learn something important, but by not doing any computation, that there is no direct measurement of lambda 3 that I can do, where direct is defined as I defined it before with the Yukawa. In the Yukawa, my cross-section depended only from the square of the Yukawa, boom, classical square. This one is a quantum thing, because you are interfering diagram which has no lambda 3 with diagram which has lambda 3. So it's a quantum measurement. There is interference. Okay. So this is it looks like a detail, but it's not a detail. Okay. It's actually important. Okay, in the way we think about it. So so this is a kind of internal background, if you want, right? When we look for TT bar Higgs, we have a signal and we have a background, right? So we separate them classically. Is the square of the sigma of one process plus the square of the other. So it's a classical sum of squared of amplitudes. Here, you will always have an intrinsic background inside that interfere with what you would like to have in your signal. You will always have this term. Okay? And also this one. Okay? So first complication is not really a direct measurement. In this specific sense. The second, so let me do now. Let me talk about how we're gonna compute this, right? So now the question you might have is, okay, now there is a box. It's complicated computation. People have done it, no problem. But you might wonder, right? In the single X, the X effective theory shrinking to a point, this loop here, or this loop, worked very well in single X. So you might wonder, does it work well here also? And what is your guess? How, in your opinion, will work if I shrink, I take the infinite top mass limit here? How this is going to work? So I add 2, right? The empty to infinity limit. I will do something like this, plus this, right? And then I compare with my full computation. What do you expect? Well, it doesn't look too good already, right? Why? Well, because first of all, we proved that it was working well for one triangle. We never talked about boxes. So I don't know, first of all. Second, remember that this works okay in the region where the Higgs mass is smaller than the top mass, right? But this is not an Higgs on shell. This is a Higgs off shell. So for this Higgs, actually, this plot is not any. So instead of saying I put the mass on the Higgs here, instead of putting mass, I put the virtuality of this Higgs, Q squared. Okay. Then this guy doesn't know that this is off shell, this one. So I can use this plot to weight or estimate how well my large top mass limit will work. So if so what is the minimal virtuality of this one? The minimal will be 250, right? Because I have to produce two on-shell Higgses. So I'm already 250, I'm already here. And then I will never produce two Higgses just at threshold, because the cross-section is 0 at threshold. It increases, and it has a maximum value at around 400 GeV, which is here. Okay, so I mean, to start with, this diagram, which worked very well in single Higgs on shell, will never get the right thing here, where the most of the cross-section is. Is that clear? Okay, so from here, I already know it doesn't look good, and from the boxes, even worse, right? I mean, it's not clear at all that it will work. So now I'll show you the plots. This is a question that people ask themselves some time ago. So this is the invariant mass plot, right? So this is a distribution of invariant masses of the two Higgses in double Higgs production. So you build a distribution, you run a Monte Carlo, and you check where the events are. So the blue line, the blue dotted line, is the full theory, is the theory with the top in it. And as I told you, the peak of the cross-section is around 400. The red is the theory where I shrink the top. And you see, it's completely different. Okay? I mean, it doesn't look at all like what is the true one, right? And the other thing you immediately see, that even in this observable, you see the problem of the EFT, because the tail of the distribution, instead of going down like that by power counting, let's say, then it's not flat, right? So it violates unitarity like a rock, okay? And that's coming from this diagram. So this diagram grows with energy in a wild way. So you get the tail, which is flat and totally unrealistic, right? So that's not a good way. And then if you play the game that we played last time with adding one extra jet, and then I look at the PT of the jet here, or the PT of the pair, I see that the full theory and effective field theory start to be different at 50 GeV. Nothing, right? I mean, there is no region where the two theories match in any case. So this tells me that it tells me two things, right? One, don't use the EFT. The approximation, let me call it approximation. Two, I will be very sensitive to new physics in the loop, because new physics in the loop is my effective field theory. Now is a new physics, right? So I will be sensitive. So this is a bad thing, no? Because it means that I cannot use this, which is easier. But this one is good, because I'm sensitive to new physics in the loop. Yes, heavy new physics. Yeah. So imagine I have a quark at 1 TeV or 2 TeV, and I don't have enough energy to produce it. But the quark will run in the loop here also, right? There will be a quark here. So this will modify this process. How does it modify? Well, the quark is very heavy. I use my effective field theory to describe it. Okay? Then we'll have a coefficient in front. The coefficient will be small because it will depend on the mass of the square, 1 of the mass of the square squared minimum, okay, at the loop, at the amplitude level. So it's a small correction. However, the difference in shape is enormous because I get it from here. So even if the amount, now this is exaggerated, but imagine that you add a very small signal to the blue curve. This signal enters in a different way in the first mean and the last mean. In the first mean is small, right? In the last mean is large. So by correlating all the means, you are sensitive to a very low intensity signal because the shape is very different. If the shape was the same, then you would not know if the difference you see is only coming from the standard model uncertainty, for example. But if the shape is different, then you can get rid of that. So there are good and bad aspects of it, and that also something that we're gonna use. Okay, so this operator is a good one, but then again, right? I will have to play my game in a fair way, and now comes the major complication for double X, and the reason why it's really difficult. So the cross section for this, I told you already, I think. So cross section for 1x is 50 picobars, and cross section for double X is 50 femtobars, roughly. So you go down by 3 orders of magnitude, very few events, very rare process. So that's the first difficulty. Then both x's have to decay to something that you see, the rate goes down, very difficult, very hard. But now, let's say that we are not worried now by experimental difficulties. It's not, let's say, our job right now. Our job is to say, well, imagine that our friends are able to give you a cross-section measurement. Okay, so how does the cross-section measurement depend on lambda? We want to extract lambda from it, right? So I measure sigma here experimentally. Now it's a quadratic function of lambda. So I measure this I calculate, and then I extract lambda. Okay, so this is what I'm doing here. I'm plotting how the cross-section of double X changes if I vary lambda. Okay, here. So if I take lambda of the standard model, I'm here. And then I change lambda, I get a quadratic function of lambda. And my cross-section changes. So how much I'm sensitive to variation of lambda? Well, is the derivative, right, of these curves around the standard model. This is how sensitive I am. If it was flat, I'm not sensitive at all. I change lambda, and I measure always the same thing, right? So I cannot extract lambda. So the highest is the slope of the curve, the best it is for my measurement. So if you see that I can also produce 2 Higgses in TT bar, right? In this production, I produce 2 Higgses. But there, you see that it's completely flat. I mean, very much flat. So what I do, but changing lambda does not do anything. So I cannot extract lambda 3 from TT bar Higgs, even also because the cross-section is so small that it's very hard. So the main production is GG2X, which is here, and the slope is not bad. Now you also see something quite interesting, that it goes down. So the cross-section goes down if lambda increases. How come? How come? So if I increase lambda, cross-section goes down. Why? I mean, I made a mistake in the plot. Hopefully not, right? What is your explanation? Let's see if you followed. It's not linear. No, it's linear. I mean, that's, I mean, this is for sure like that, right? I mean, yes? Yeah, right? Because effectively here, right, this guy is negative. This thing here is less than 0. It's an interference. Can be anything. Okay? So this is less than 0. And it's actually, there is actually a large cancellation between the two that makes our life complicated even, right? In fact, you see that there is a minimum, okay, here. So each of these curves have a minimum, not all of them. So these diagrams are actually, there is a minus sign here, so to speak, and it's always there for any process, right? So again, in fact, you can trace it back to the structure of the standard unitarity in the standard model. This process does not violate unitarity in this thing because there is no enhancement in energy, but it goes back again to the fact that you must have a minus sign there in the standard model. Okay, so this one I wanted to say why it is difficult, and then let me finish. I need 1 more minute, then we are, for once, we are done in time, almost. And so now I have the sensitivity of lambda, okay? So I want to measure sigma, and I will get a bound on the values of lambda with an uncertainty, okay? And then you say, yeah, but if I'm doing the standard model, I know where lambda is because everything is locked. Okay, so I'm only testing the standard model in this way. I cannot have anything different from the standard model because as I was telling there, lambda 3 is equal to lambda 4 equal to lambda equal to the mass of the X. So how I deform the standard model to make this a real measurement of something independent, I add an operator, which is called O6, which is this operator here, which unlocks, so this operator unlocks the mass of the X with lambda 3 and lambda 4, which are still locked in dimension 6. Okay. So the mass of the by adding this operator, I make the mass of the X independent from lambda 3 and lambda 4, but lambda 3 and lambda 4 among themselves are still linked among them. I don't unlock the two. Okay, so this is called O6, is a quote unquote a famous operator because is the one with which we modify the self-coupling. So that's the way we are doing. But then, of course, then the question is, okay, but if you modify this one, then you have to go back and look all the diagrams where the other operators enter, right? The chromo, the Yukawa, and the GG, right? This one. So I will need to do the full computation again, okay, which is shown somewhere here, right? So you add all the operators in your game, and you need to, now you understand that to determine lambda in the EFT, I need to know all other operators very well, right? I have to have constrained all the Yukawa, the GG, and so on with single X production very well, and then I can access lambda 3. Because if I don't know this coupling very well, I will never be able to determine this one. Is that clear? So it's a really a hierarchical knowledge, and that's the reason why when we think of the standard model of the EFT in general, but in a standard model measurement, it's really a pyramid of measurement. It's not like you cannot access information alone, right? You always to think globally that in order to get to that point, you must have determined all the other operators very well before. So it's really a team build, a team effort from many, many directions. Okay. So okay, this is a bit complicated maybe, but basically it shows how well you need to know the other operators to be sensitive to lambda 3. Okay, so this is a bit technical, but I mean, of course, you can answer, right? You put a yt arbitrary and imagine if I know yt at 10%, how well I can measure lambda 3 and so on. And you make a sensitivity plot together, and this shows that you need to control all the other coupling rather well before you are able to say something about lambda 3. So this is a real challenge for the NHC. I noted down how all the coefficients in the notes. I don't want to do it right now, but I mean, I really hope that you got the logic. So I'll not talk about SMECT again tomorrow. So if you have any questions now or later, I'm available. Thank you. Right. No, I didn't. So there are other operators that enter. What is like this one, for example, or this one. Right. So these operators enter in the determination of the X subcoupling, but at the end, okay, you can show that you only need a linear combination, and this linear combination of these two operators depends on one coefficient which is called CH, which is there also in this plot. This all age is actually CH, which is a global rescaling of all the single coupling of the X. Okay, so it's like you shift by the same quantity all the single X coupling to anything else. Okay, so that operator we have control from single X. In fact, I think is you can see it even from here. The green one, you see the green one. So continuous means that you don't know. So this is the range of your determination. Dashed means that we excluded it. And you see from above that you hit the green line after all the others. So a global rescaling on the X is quite well constrained by the global fit on the kappa. So it's not let's say the most of the problem. No, is not the widest. Is the one. So this is sigma over sigma standard model, right? Okay. So that's your measure divided by your. So you go from above. So when your limit improves, you go down with this line. So the purple here is the trilinear. And you see that basically all other curves on the other coefficient, the dashed line is below, apart from here, let's say. So being below, it means that you are not sensitive to it. So you determine it well enough that for the determination of the purple line, it doesn't influence your determination. And you see that for CH, you're down here. So you will first hit this one, for example. So it's not the leading behavior, the leading the leading limitation. Okay. So in other words, the coefficient in front is small with respect to how well we know the scaling of the global parameter in the Higgs cross-section. Okay, so it's a bit technical now. But, yes. Yes. Not quite. Not quite. I mean, that's the way we phrase it. But it depends on the relative phase between the Higgs coupling to the bosons and the Higgs coupling to the top. Okay, truly, because so if there was a phase between these two coupling, if it was the phase between these two was not the standard model prediction, then you would violate unitarity. And this you can prove yourself, if you want, by computing this. Okay, so in the standard model, there are 3 diagrams. Okay, here. So this is a B. So if the top mass is 0, if your fermion mass is 0, then this diagram is not there. And these 2 diagrams are unitary. Right? They don't grow, each one of them grows with energy, but when you sum them, the growth cancels. And this is a gauge interaction. This is a gauge cancellation. Right? And it's also related to CKM matrix, because here you can have S and D. You can prove, right, that by summing these 2 diagrams, you cancel the growth in each one of them. Right? And that's a textbook example of the fact that our, the standard model, you need this vertex, right? You need SU2 to have unitarity in the standard model, right? So this we know in school, in the standard model classes. So if the top has a mass now, you add the mass, actually there is a leftover divergence growth in energy, which goes like m top square root of E over V squared. Okay, so this diagram, if the top is massive in the S wave channel, in the partial wave decomposition, this grows with the mass of the top times the energy, square root of the energy divided by V squared. Sorry, like that. If you add this one, in the standard model, it cancels. But now you see that it cancels. I mean, there is a, this will be like, I don't know, like plus something which grows. And this will be minus something that grows. Okay? But now if you change the phase of this coupling, or this coupling, this doesn't, you change the phase here and it doesn't cancel anymore. So from this simple argument, you know that the phase of these 2 is fixed in the standard model. The relative phase. Okay? So if you change it, you're going to screw it. And this is exactly the phase which enters in the X to gamma gamma, right? It's the same thing. Because here you have X in gamma gamma, this diagram, minus, right, this diagram. So now if you change this phase, this doesn't cancel anymore. So that's not free. In other words, it's not free in the standard model. You cannot change it, keeping unitarity. Unitarity tells you what is the relative phase of the X coupling to the bosons or to the fermions. There is another example, and then I stop. This is only academic, really. But there is actually one example, which is not academic, which is kind of interesting. And I studied it when I was a student, so I'm very attached to it. And it's called single top plus X. Okay, so you have you can produce a top alone in a standard model through an electroweak interaction. You're not obliged to produce a T bar all the time through strong interactions, but you can fuse a B from the one proton with a light quark by exchanging a W in the T channel. So this is called single top. And it has a cross section of about 200 picobar, 250 picobar. So compared to TT, which is 1 nanobar, is 4 times smaller than NC, but it's not, I mean, it's larger because the TT bar is a very large cross section. So you have a lot of single tops. So now people, when back 30 years ago when I was a student, no, a little bit less, come on, well, whatever. So people said, well, you do TT bar Higgs to measure the Yukawa coupling, and after all, you only have 1/4 of the event. Maybe we can measure the Yukawa coupling of the top and the X also from here, no? Because we can emit a X here. But in fact, you can emit a Higgs here, but also you can emit a Higgs here. Okay? And now, and that was why, was so exciting for me, right? Was, well, you realize that there is a sensitivity to the phase, to the relative phase of the Yukawa and of the W. So this is actually the LHC realization of this academic exercise that you do during the standard model course. It's really, this happens. It has been measured. T single X plus top is measured together with TT bar X and LHC. So it's not academic anymore. It's measured. Okay? And this process is sensitive to the relative phase. In fact, and this I realized by my own experience because I got it wrong, as usual. The first time you compute, you flip a sign, right? And I was getting enormous cross sections, right? So I was super excited because I was getting very large cross section for single X. So I went to my advisor and said, "Well, look, everybody thinks it's small, but it's very large." And then he said, maybe it's too large, right? And then we realized that, right, by doing so we did a computation and we checked that unitarity obliges you, and actually this tells you that in the standard model, you have this relation built in. So if you break this grows with energy, right? Which I know from the AFT, because I add an operator which breaks it, but now since I add an operator, this breaks unitarity, because I have a 1 over lambda squared. So if I think in terms of its math, I know that if I break this, it will grow. Not all processes grow, but this one grows like crazy if you flip the sign, because the interference is very large and negative. Was this your question? Because I think I got drifted away by. Okay.